So I hope you've watched my sine and cosine function and cosecant and secant functions. We're going to talk about tangent, y equals tangent x, and y equals cotangent x, the parent functions. And then after that, we'll talk about transformations. But right now, we're going to talk about this function and this function. And hopefully it won't take too long. If we do this point transfer thing like we did with the other functions, we would end up finding the following. Actually, I guess I want this to go a little further because of the width. So let's grab this. Nope, it's not going to work that way. Yeah, that's better. Pow! All right. So those are that's my theta or x-axis, my angle measures, and these are the heights. And really, they're not heights like the other ones. This y is really the y over x in the unit circle, but it's going to be the output of our function from tangent. And so here's what tangent looks like. So the tangent of 0 degrees, if you think about unit circle, it's this point, and that's 1, 0. I take the ratio of the y over x, so I get 0 over 1, which is 0. So tangent x has a point at the origin, 0 for the angle measure, but 0 for the y value as well. And then over here, let's say here, I have pi over 2. And so if I look at pi over 2, that's 90 degrees, and that's at the point 0, 1, right? 0, 1 on the unit circle. But if I take the tangent of 90 degrees, or pi over 2, I'm going to take y divided by 0. I'm sorry, y divided by x, which is 1 divided by 0, which is undefined. So once again, like in secant and cosecant, we get undefined as a value for our height, or our y value, at pi over 2. What that creates is this asymptote, like we had when we were doing rational functions. Because my point, pi over 2, comma, undefined, can't be plotted. There is no y value. So I go to that value, there's no y value, so there are no points at pi over 2. Similarly, at negative pi over 2, and 3 pi over 2 for that matter, I get undefined for my y value, or excuse me, for my tangent as well. So over here, at negative pi over 2, I also get an asymptote where there are no points. Okay, so that's what's happening at those values. And we're going to fill out one more set of, well, one more and then a discussion. So here we go at pi over 4 and negative pi over 4. Okay, and if we look at the tangent function there on the unit circle, those are 45-degree angles, right? Pi over 4. And so we're talking about radical 2 over 2, comma radical 2 over 2. And then negative pi over 4 is this guy, and that's going to be radical 2 over 2, comma negative radical 2 over 2. And when I take the ratio of the y over the x for tangent of pi over 4, I'm going to get radical 2 over 2 divided by radical 2 over 2, which is 1. So at angle of pi over 4, I get a value of 1. Let's say that this is 1, and this is negative 1. And so I have a point here and a point there. You might think it looks like a line. We don't have enough data points, but we'll get there. And then if I look at negative pi over 4, which is this angle, I will get negative radical 2 over 2 divided by radical 2 over 2, which is, of course, negative 1. So that's this point. And at this point in time, I'm going to change colors for the tangent function, but we're going to get a couple more points here. We're going to get pi over 6, which is approximately here, okay, and negative pi over 6, which is approximately here. So that's these guys. Pi over 6 and negative pi over 6 are these values. 30-degree angle here, or pi over 6, and negative pi over 6 is a 30-degree angle, reference angle here. And so what do I get for the point at the intersection of the unit circle with the terminal side? I get radical 3 over 2, comma 1/2, and radical 3 over 2, comma 1/2. Now if we do that ratio, we get 1/2 divided by radical 3 over 2. That one's negative. and the other one has this negative y value, but that's okay. We know that the negative angle is a negative value at this point, I hope, in that quadrant. So 1/2 divided by radical 3 over 2 is the same as 1/2 times 2 over radical 3, which is equal to 1 over radical 3, which is equal to radical 3 over, I'm sorry about the running out of space and I'm going around in a circle. Radical 3 over 3, hopefully we understand that radical 3 is about 1.73, and 3 divided into that is 0.6 something, 1.5 something, blah, blah, blah. Okay, all right. So pi over 6 turns out to be, as I said, 0.57 and change. So it's somewhere around there. Okay, somewhere like right there. Okay. Now, on the flip side, that's somewhere over here on the negative side, somewhere in there. Okay? Let's erase a bunch of this scratch work, and let's look at a 60-degree angle, or pi over 3. That's that guy or that guy. And so we're talking about the same values as before, except we're talking about radical 3 over 2 divided by 1/2, which is radical 3 over 2 times 2 over 1, which is radical 3 over 1, which is just radical 3, which is 1.7 blah, blah, blah. And so 1.7 blah, blah, blah is like up here. Okay? Now, we don't know any of the other measures, but if we put them in our calculator and plotted a whole pile of points, we'd end up getting something that looked like, and again, I'll change color so we can see this, get something that looks like this. Okay? So it kind of looks like this. It kind of comes up, and then it flattens out a little, and it shoots up again. All right? That is one segment or section of the tangent function, or the function y equals tangent x. What happens, though, is it's happening because as we travel around the unit circle, right, we're at 0, we're going towards pi over 2. As we get closer to pi over 2, note that since tangent is the tangent of an angle is y over x, here the y value is very, very large divided by a very, very small x value. Again, very, very large y value, very, very small x value. And so that becomes a much larger number. And as we get closer and closer to 90 degrees, like instead of pi over 2, think about 6999 pi divided by 14,000 pi. That's not quite pi over 2. That's almost pi over 2, but it's wicked, wicked close. Well, this is really, really tall compared to this tiny, tiny little x value. So we go shooting up not the y-axis, but along this asymptote. And on the other side, when I approach negative pi over 2, it's happening down here as well. So what ends up happening, I'm going to redraw this, but not as nicely. It's going to be a sketch. We end up getting this. And this. Okay? But then our tangent function looks sort of like this. And then there's another one over here. And there's another one over here. And in between we have these asymptotes, which I described earlier, and it just repeats. Okay? It just keeps going. It keeps going that way, and it keeps going that way. And they look like that. And they go right, that first one goes right through the origin, or the middle one goes right through the origin. So if we scroll back this way, there's one thing that's very, very important to point out, and I'll bring it up again. The other functions, y equals sine x, cosine x, cosecant x, and secant x, all have a period of 2 pi. Period equals 2 pi. For this function, tangent, the period is no longer 2 pi. The idea is that from here to here, purple. From here to here is what distance? Well, from here out to here is pi over 2, and from that, or from the y-axis in the other direction, is pi over 2. Pi over 2 plus pi over 2 is pi. So this is a distance of pi. And if we go up here, realize that if this is pi, and then this is pi, and this is pi, the question is how long do we have to travel before the function repeats? Well, we have traveled from here to there, and then it repeated. And then we traveled from here to there, and it repeated. So the period of tangent, the period of the parent function, tangent, is pi. And so that's different than the other functions. Now, for the reciprocal function of tangent, y equals cotangent x, I guess one way to say it's quite the opposite in some respects. It's the reciprocal, and this is what happens. Because it's reciprocal, wherever tangent, for instance, let's go here, wherever tangent had an asymptote, because we had some sort of 1 over 0 for this point, negative 1 over 0 for that point. But for cotangent, when we take the reciprocal, we get 0 over 1. So instead of an asymptote at that point, we get a 0 at that point. And then, remember tangent, we had this 0 value. Well, if that was a 0 value for tangent, when I take the reciprocal of that value for cotangent, I get 1 over 0, which is undefined. So for cotangent, at that same location, angle equals 0, I get an asymptote instead. And so what ends up happening for cotangent, y equals cotangent x, is that wherever there was a value of 0 for tangent, we get a value for an asymptote for cotangent. And whenever there was an asymptote for tangent, we get a 0 value for cotangent. And so our function looks sort of like this. Maybe I'll draw this one better. That one looks a lot better. And then there's an asymptote here. This is at pi over 2 now instead of negative pi over 2. Instead of an asymptote, I have a 0 value. And this one, I have a 0 value at pi over 2 instead of an asymptote. The asymptotes occur at pi and negative pi instead of at the pi and negative pi over 2. Now I want to point out what I would call anchor points, how you can figure out what is what with these two functions. The anchor points are these guys. Let's use white. The anchor point is this for tangent. That's 1, and the other one happens at pi over 4, comma 1. It's this point. So anchor points for y equals tangent x are 0, comma 0, and pi over 4, comma 1. You could also say negative pi over 4, comma negative 1, but that's fine. But you only need 2. If you work these 2 points when you're working on translations and whatnot of these graphs, these transformations of these graphs, you should be okay. All right. For cotangent, I haven't much thought about it, but it's probably going to be that's going to be pi over 4 is going to be 1, and pi over 2 is going to be 0. That's this point. So it's going to be that point and this one here. Okay? Well, at least that's what I would use when I'm dealing with the transformation. So that's tangent and cotangent and why they look the way they look.